So welcome to the session on verification. My name is Gautam Kaki. I'm session chair. The first talk is from Chenglin Wang on solving conditional linear recurrences for program verification, the periodic case. Chenglin.
Morning, everyone. It's my great honor to be here to introduce our work on recurrence solving and its applications on program verification. I'm Chenglin, a PhD student from HKUST, supervised by Professor Fangzhen, who is also the second author of this work. So before diving into the technical details, I would like to introduce some motivations for the recurrence analysis. So most of us are familiar with Area VM, which is a really powerful and popular compiler framework. So I tried to ask ChatGPT which components in it make use of recurrence analysis. And here is the answers. So you can see passes like loop virtualization make use of recurrence analysis. So actually, if we compile our work using any Area VM-based compiler, we are very likely to be benefit from it. And also note that all the listed passes focus on code efficiency, but in our work, we focus on its applications on program verification. So for verification, Professor Lim proposed a method for translating any C-like program into a set of first-order language, which can be fed into SMT solvers directly. This is the example, and the key point of the translation is that a loop is translated into a set of recurrences, but current SMT solvers doesn't dealing well with such a recursive definition. So what we need to do is to remove them by computing closed-form solutions for them. But current recurrence solvers are still limited in dealing with the conditional recurrences, like the one in the running example. So for example, Mathematica is one of the most powerful algebra systems in the world. It provides a function called rsolve, which is really powerful when the recurrence is non-conditional. But if they encounter the conditional ones, they will just give up. I tried to give it the recurrence in the running example, which is conditional. Then it just give up and return what I type in. But a closed-form solution does exist for this conditional recurrence. And here is the result produced by our tool. And then together with other actions in the previous slide, the SMT solvers can prove the correctness of that assertion. So here is a short summary for our contribution. So first, we propose a method for solving what we call periodic linear recurrence. And then we extend this result into two much more complex settings. And finally, we also implement prototype tools and apply it in some verification tasks. And the result shows that with this more capable recurrence solver, more programs can be verified. So here comes the definitions of conditional linear recurrences, so for which we want to compute a closed-form solution. So each conditional linear recurrence, it consists of some branches, and each branch are guarded by some condition. And if this condition is satisfied, there is a corresponding linear transition. So that's why we call such a recurrence conditional and linear. So for the running example, we will also represent it in this matrix form. But before we try to solve the most general conditional linear recurrence, let's first see how to solve a much simpler version and try to gain some insights from this process. So periodic recurrence, we just replace the conditional part with these modular operations. And this is then a concrete example. So for solving this example, let's first run it for several iterations. So the first table of this row, the first row of this table, it denotes the iterations of the loop or the recurrence. And the second row, it denotes in the corresponding iteration which condition is satisfied. And the last row, it just records the index of the second row. So from the table, we can see the index sequence in the last row is actually periodic because it contains 0, 1, 0, 1, 0, 1. So the effect of this recurrence can be summarized in every 2 iterations. So that is, if k is an even number, then the sk should be equal to this term. Otherwise, it should be equal to this last term. So what we need to do next is to compute this matrix power symbolically. So for that purpose, we resort to the Jordan normal form, which is actually an extension for matrix diagonalization. Many algebra systems like SymPy, Mathematica, they all provide these functions. So for the running example, we need to solve this matrix power symbolically, and this is the result produced by Mathematica. And finally, we just need to replace this matrix power into the formula we derived in the previous slide. And then finally, we will achieve the closed form solution. And here is the formal result for computing closed form solutions to periodic recurrences. So the reason why a periodic recurrence is solvable is that the order of each satisfied condition is periodic. So the final transition, the effect of all the transition can be summarized by just multiplying those matrices in different branches in order. And then the closed form solutions can be obtained by computing matrix power symbolically. So this suggests that for any general conditional linear recurrence, if the corresponding order is periodic, then we can solve a closed form solution in a similar way. So here comes the most important concept in our paper. That is what we call index sequence. So intuitively, the index sequence is just record the order of the fire conditions when this recurrence is used to generate the whole sequence. So for the running example, the index sequence is actually the this last row of this table. That is the whole index sequence. They are 1, 1, 1, 1, followed by infinite number of zeros. So recall that if the index sequence is periodic, then we can compute a closed form solution as what we did for the periodic recurrence. But unlike the periodic recurrence, whose index sequence is known. So we don't know what the index sequence of a general conditional linear recurrence looks like. So we decide to adopt a generate and test method. That is, we first try to run the loop or the recurrence for the first several iterations, and then recall the order of the fire conditions, which is actually some prefix of the whole index sequence. So, and then we guess the periodic segment from it. So for the running example, we will start from x0 and try to run it for the first 2 iterations. And because the index sequence is 1 and 1, so we just guess the periodic segment is 1. That is, we will assume the whole index sequence is 1, 1, 1, 1, 1, which means the second condition is satisfied. So the second matrix is always applied. So for the current iteration, we will compute the closed form solution to sk to be equal to k. But for now, this closed form solution is just a hypothesis because we have some assumption on the index sequence. And the assumption is that the index sequence is 1, 1, 1, 1, 1. So which means the second condition is satisfied. So the validation condition is set up by replacing the sk in the second condition with this hypothesis closed form. And then establish this validation condition, which is obviously it doesn't hold. And the smallest k that violates this validation condition is 50. So in the next iteration, we will restart this process from x50. But for now, we can still conclude that for all k less than 50, the closed form solution is k. And then for the next iteration, we still run it starting from x50 and see that the index sequence is 0, 0, 0. So for now, we assume the periodic segment is 0. That is, the whole index sequence are 0, 0, 0. So which means the first matrix should be applied forever. So we can now get another closed form solution. And again, we need to verify this result. So because the assumption is that the whole index sequence is 0, 0, 0, so the first condition should always satisfy. So we set up this validation condition, which obviously it does hold. So we can conclude that the whole closed form solution is something like this one. Previously, we just considered the case where the initial values are known, so that we can generate some prefix for the index sequence. But if the initial values are all unknown, then we cannot even get such a prefix. So to handle that case, we also propose a method, but due to the time limit, we can only show some examples to show the capability of our tool. So for this part, for more technical details, you may refer to the original paper. Our experiment has two parts. The first part where all the benchmark program has known initial values, and the second part, all the initial values are unknown. To compare, we compare with three other tools. The first two, ICRA and VIP, they also perform recurrence analysis, but with some different approaches. In the last row, the very apps, it ranks first in the rich safety check in SVCon. And in this table, in each cell, the number on the left, it denotes the number of safe program. And the number on the right, it denotes the number of unsafe ones. And the program on the right is some example in this benchmark. So this table concludes the results where all the benchmark program contains unknown initial values. And the notation is similar to the previous table. And the program on the right is an example in the benchmark. So that's all for my talk. Thank you.
Anyone? Okay, I'll start. So it does seem like there is a close connection between closed form computation and inductive invariant inference. Is there one? So is there any connection with the closed form inference and inductive invariant inference?
What difference?
Inductive invariant inference.
Inductive.
So you're computing the closed form solution for loops, right?
Yes.
So how does that relate to the inductive invariance for the same loop?
Sorry, I don't quite understand the last sentence.
Okay. Maybe we'll move on to something else. Any other questions? Did you try integrating this solution into the Mathematica? Because that's how you started your talk, right?
So for you mean I need compare with the Mathematica, right?
The Mathematica. So your initial, you tried the same solutions in Mathematica, and you wasn't able to work. So were you able to integrate your solution into?
Yeah. For example, for this non-conditional one, my tool can return the same result as the Mathematica. But if the condition, if the recurrence is conditional, then the Mathematica just give up.
Okay. Any more questions? All right, let's thank the speaker again.